this video, we will be discussing about maximum employees to be invited to a meeting. A company is organizing a meeting and has a list of n employees waiting to be invited. They have arranged for a large circular table capable of seating any number of employees. The employees are numbered from 0 to n minus 1. Each employee has a favorite person and they will attend the meeting only if they can sit next to their favorite person at the table. And the favorite person of an employee is not themselves. Given a zero indexed integer array favorite, where favorite of I denotes the favorite person of the ith employee, return the maximum number of employees that can be invited to the meeting. So what they are saying is that in the input, we are given this array, which is denoting a person's favorite employee, right? So basically, if I give the indices over here, 0, 1, 2, 3, so this is telling us that this person's favorite person is person 2. This person's favorite person is person 2. This person's favorite person is 1, and so on, right? So now we are given a circular table on which infinite number of people can sit, right? Now we need to make all of these persons seated on this table such that each person sits next to its favorite person, right? So for example, here the favorite person of 0 is 2. So 0 will only sit on the table if it is sitting next to 2, right? So if I just write it like here, so person 0 has to sit next to person 2. Then person 1 has to sit next to person 2, right? Then person 2 has to sit next to person 1. And then person 3 has to sit next to 2, right? So can you see this is some kind of a directed graph over here? Why a directed graph? Because 0 is dependent on 2. It will sit only when it is sitting next to 2, right? So that is why this is a directed graph over here, right? So as you can see, 0 will sit next to 2, 2 will sit next to 1, 1 will sit next to 2, and 3 will sit next to 2, right? So this is what the graph is, right? So now we need to make them seated on this circular table, right? So see, if we see at this, we can make the 0 person sit here. Now it has to sit next to 2, so we will make 2 seated here. Now 2 wants to sit next to 1. So we can make 1 seated here. Now only 3 is remaining. Now this 3 has to sit next to 2, right? But if you see on a circular table, a particular person has only two sides, one on its left and one on its right. So basically, a person on this table can only sit next to two persons at max, right? So since here, this person 2 is already sitting with 0 and 1. So this 3, if it wants to sit next to 2, either it should come here or it should come here. But if it comes here, then the condition for 0 and 1 will be dissatisfied, right? So that is the reason this person 3, we cannot make it sit on this circular table, right? Otherwise, in some other scenario, what we could do was that instead of 0, we could make person 3 sit here. Then in that case, this 0 person won't be able to sit anywhere on the table, right? But we do not need to identify that what all persons can sit on the table. We just need to identify that what is the maximum number of people that can sit on the table, right? So either you put 0 here or you put 3, the answer is any which way is going to be 3, right? So we can make any of them seated here, right? Then if we look at the second example, let me give the indices. So here 0 has to sit next to 1, 1 has to sit next to 2, and 2 has to sit next to 0, right? So this is what the arrangement is. So on the circular table, I can make them sit like this, 0, 1, 2, right? 0 wants to sit next to 1, 1 wants to sit next to 2, 2 wants to sit next to 0, right? So here we can put all the people on this table, so the answer will be 3. Then if we look at the third example, 0, 1, 2, 3, 4, so 0 has to sit next to 3, then 1 has to sit next to 0, 2 has to sit next to 1, 3 has to sit next to 4, and 4 has to sit next to 1, right? So now, this is my circular table. Now if I see 0 has to sit next to 3, right? So I'll put 0 here, 3 here. 3 wants to sit next to 4, so I'll put 4 here. 4 wants to sit next to 1, so I'll put a 1, and 1 wants to sit next to 0, so it is besides 0 only, right? But we are still left with 2. Can we accommodate 2 anywhere on this table? No, because all of these are already connected. 0 with 3, 3 with 4, 4 with 1, and 1 with 0, right? So we cannot put 2 over here. So in this particular case, our answer will be 4, right? So now here are few observations which you would have already seen. That one is that each person can sit only besides two other person, right? Then the next thing is that there will always be one outgoing edge from each of the node, only one. Why? Because we have indices over here. Indices will always be unique, right? So from each of the node, you will always have only one outgoing edge. You can never have a graph like this, right? Because zero index is only one over here, so it will always have one outgoing edge, right? Then the third observation that you can see over here is that all of the graphs have a cycle. Here also we have a cycle, here also we have a cycle, and here also we have a cycle. Why? Because we always have n number of nodes and n number of edges, always, right? So that is the reason our graph will always have a cycle, right? So now, if you see these two examples, when I had a cycle, I was able to put exactly that cycle on my circular table and I could accommodate all the persons in that, right? And similarly here, this was a cycle. So I was able to accommodate all the persons which are part of that cycle on the table, right? But this person, which was not a part of cycle, I couldn't put this one, right? So, can I say that if I just identify the cycles in my graph and their lengths, then that would be my answer, right? So, see, it is not necessary that our graph will always have one cycle. There can be multiple cycles if we have multiple components, right? Basically, if let us suppose my graph is like this, right? So this is my entire graph, right? It is not necessary that these two will always be connected with each other. We can have multiple components in our graph, right? So in that particular case, we are having two cycles. One cycle is this one and one cycle is this one. So in this particular case, as you can see, we can only put one of these on the circular table, right? So which one you will put? Obviously the one which is having greater cycle length. Why? Because we need to maximize our answer, right? So here the cycle length is 1, 2, 3 and here it is 1, 2, 3, 4. So we will put this one on the circular table and our answer will be 4, right? So the observation that we made was that if we identify all the cycles and their lengths from our graph, then whichever is having the maximum length, that is our answer, right? But if you look at the first example over here, here also we had a cycle. So as we saw here that we can only put cycles on the circular table and not the extra nodes, right? But here, in addition to this cycle, we were also able to put the extra node 0 on the circular table. Why is it so? Because here the length of the cycle is 2, right? Here the length of the cycle is 2, so these two are sitting next to each other. So for this 2 and 1, we still have one position remaining over here, and here we can put other nodes as well, right? If you see, this 2's in degree is only 1 in this cycle, right? But we can have one more in degree from anywhere. Either we could put a node 0 or we could put a node 3, right? As I told you that on the circular table, each node can have only two persons sitting next to them, right? So if I have a cycle of length 2, then there is still one side remaining for both of the nodes where I can put some other nodes, right? So the condition is that if the length of the cycle is greater than 2, then in that case you would be able to put only that cycle on the circular table, right? So in that particular case you can just identify that what is the maximum cycle length and that is your answer. But if you have a cycle of length 2, in that case, we will have to include the other nodes as well, right? So now let's understand how are we going to include those other nodes. So if let us suppose that our graph looks like this, right? And here we have a cycle of length 2, right? And as I said, when we have a cycle of length 2, then these two nodes are still having one side vacant. So we can make some other person sit there, right? So now for this node, it has one side vacant, right? So either it can put this particular node on its side or it can put this particular node, right? If we are putting this one, then we can put this, and this entire thing we can put, right? And if we are putting this one, then this entire thing we can put. But the thing is for this node, either we can take this one or we can take this one, right? So now which one are you going to take? Obviously the one which is having greater number of nodes, right? This one. Here the number of nodes are 1, 2, 3, 4, and here it is 2. So obviously you will take this one, right? And then for this node as well, you can take any of these, right? So here both are having 3 number of nodes, so you can take any one of them, right? So whenever we are having a cycle of length 2, we can consider these components as well, right? Now, if let us suppose that our graph has multiple cycles of length 2, right? So here also we could have a cycle of length 2 and some number of nodes over here, right? So we could have this also. Basically, this entire is our one graph, right? So in this particular case, what you can do, if for these two, I am considering these two, right? So can I consider this node with its extended nodes as well, and then I can connect these from here and these two from here? I can do that, right? Basically, when I have taken a cycle of length 2 and I have taken its extended nodes, then these two nodes still have one side left, right? So if I have another similar component, what I can do is that I can make them sit to next to each other and I can make these two sit next to each other, right? And then it will be able to form a circle like this, right? And if we have a third component like this, then we can include that as well, right? So basically, whichever number of two length cycles you have in your graph, you can include them with their extended nodes together onto the circular table, right? So here, whatever is the length of this, whatever is the length of this, you can add it with whatever is the length of this and whatever is the length of this, right? So that will give you the maximum number of persons that you can sit on the table when you are considering all the cycle lengths of 2, right? So basically, the conclusion over here is that for your answer, what you will do, that if the cycle length is greater than 2, in that particular case, you will find out the maximum cycle length, right? And the cases where the cycle length is equals to 2, in that particular case, you will find out the sum of all two length cycles along with their extended nodes, right? Now, it is possible that within the same graph, you have a cycle of length greater than 2 and cycle of length equals to 2, right? But on the circular table, we can put only one cycle. Either we can put this or we can put this, right? So what we will do is that when we have identified the maximum cycle length for length greater than 2 and the sum of all two length cycles along with their extended nodes, we can take the maximum of these two and that will be our answer, right? So basically, we will be taking the maximum of these two, and that is going to be our answer, right? So this is what we need to do. Now, how are we going to solve this? How are we going to identify these two things? So if you see over here, when we have a graph like this, how can we identify this particular length? So see, if you consider all of these nodes have their in degree as 0. There are no incoming nodes to these nodes, right? All of their in degrees are 0. So we will apply the concept of topological sort over here. Topological sort over here, right? In that, what we do is that we take all the nodes where the in degrees are 0 and we put them into a queue. So basically, these four nodes, we will put them into the queue, right? And here, the in degree of the node denotes us whether the node has been visited or not, right? So when you will put these four nodes into the queue, what you will do, you will start applying BFS. You will take this node out. Now, when you will take this node out, this node's in degree will become 0 now. So you will put this particular node into your queue, right? And since we want to know that for this node, which one should I consider? So I should know the length also, right? So what we will do is that we will maintain a vector depth, right? We will maintain a vector depth, which will tell us that for each of the node, what is the maximum depth, right? So basically, for this, we will keep it as 1. For this, it will be 2. Then here it will be 3. For this, it will be 4. Then for this, it will be 5. Then here it will be 1. Here it will be 2. And then here we will get 3. Now, for this particular node, we are having two depths. One is 5 and one is 3. Which one are we going to consider? Obviously, the maximum one, which is 5. Why? Because we want to consider this particular path. We need to maximize our answer, right? So for each of the node, we will always consider the maximum depth, right? So simply what we can do is that when we have pushed these nodes into the queue, we will take this node out, right? So this will be removed and the in degree of this particular node will become 0 and the depth for this node will become 2. Then we will take this out, right? Like in the actual BFS, these nodes will be taken out first. But right now, for simplicity, let's consider this particular path. So now this is having depth as 2. Now this will be taken out, right? So this will be removed. And now this will have an in degree of 0 and the depth as 3. Then we will remove this. Then this will have in degree as 0 and depth as 4. Then we will remove this, right? So now this will have a depth of 5, right? But its in degree is not 0. We still have a node here. So this won't be pushed into our queue, right? Same thing happen for these paths also. Here the depth will be 1, here it will be 2, and when it will come here, it will be 3. So all of these will be removed, and here it will have 3, and it will take the maximum of these two, which is 5. So this will have a depth of 5, right? And same way here, 1, 2, 3, 4, 1, 2, 3, 4, right? So these all will be removed, and then here we will have the depth as 4, right? Same thing will happen for this one also. These two will be pushed into the queue, and then here you would have 3 and 3, and these will be removed, right? So now here we considered a case where we were having a cycle of length 2. Now if let us suppose that we had a graph something like this where the cycle length is more than 2. So here also, like, you could have a graph like this. You could have extended nodes here also, right? So here also you would identify the depth, right? So what would happen here? It would be 1. So here it would be 2. This would be removed, and here it would be 2. Then here 1, 2, 3, right? So these will be removed and its depth will be 3. Then these two will be removed. Here the depth will be 3. And then here these two will be removed and the depth will be 3, right? But now you need to identify the cycles. You know that for all these nodes, the in degree is not 0, so they won't be pushed into the queue and your BFS will finish now, right? So what you can simply do is that you can run a for loop for all the nodes in your graph, and you can check that wherever the in degree is 0, so that node is already visited. So there we will just move on to the next node. But if the in degree is not 0, then that means it is a part of a cycle, right? So we can run a loop to identify the cycle length. We can keep our current node over here, right? So now its favorite node is this one. So our current will become this one and cycle length will become this one, right? And then this node's favorite node is this one, right? And for this, we would have already visited it. The in degree of this node would now become 0, right? So we can say that the cycle is completed and the length would be 2 in this particular case, right? So for this, the length would be 2. Same we would do here, that this would be our current node first, then its favorite would be this node, so the length would become 1, then its favorite would be this node, length would become 2, this would be the next favorite node, length 3, and then we would come back here, this would be already visited, length would be 4, and this is our cycle. And same we would do here, right? So now what you can do is that you can check that if the cycle length is greater than 2, right, which is in this particular case, so you can maintain some variable to identify the largest cycle length, and in that you can take the maximum of that variable and the length of this cycle, right? And when the length is equals to 2, in that particular case, what you will do, you will take the sum of these two, 5 plus 4, because this number is telling us that what are the number of extended nodes over here, including this particular node, right? And same way here also. So we can just add these two. 5 plus 4 will be 9. And then here also we can add these two. 3 plus 3, 9. Sorry, 6. This will be 6. So these two will be added together in some variable. 9 plus 6 would give you 15, right? And this one is 4. So basically, then you can take the maximum of these two, and whichever is the maximum, that will be your answer, right? So this is how we are going to solve this problem. Now let's look at the code. So first of all, let's take the total number of employees, which will be n. That will be favorite dot size. This is basically the total number of nodes that we have in our graph. And then we will create a vector for storing the in degrees of all the nodes. Let's name it in, and its size will be n, and initially the in degree will be 0 for all the nodes, right? Then we will run a for loop of I starting from 0 going till n, and then we'll do I plus plus, right? Now inside the favorite vector, whatever is its index, from that index we have a directed edge towards its value, right? So whatever is the value, its in degree will be increased by 1, right? So in the in degree vector at the index favorite of I, what we will do, we will increment it by 1, right? So now we have updated the in degree of all the nodes. Now what we want to do is that for our BFS, we will push all the nodes with their in degree as 0 into a queue, right? So first we will take a queue which will store integers, and then we will run a for loop of I starting from 0, I less than n, I plus plus, and inside this we will check that if the in degree of I is equals to 0, then in that case in the queue push this particular node I, right? So now that we have done this, we will start our BFS. So while our queue is not empty, right? What we will do is that we will take the front node, which will be our current node, queue dot front, and then we will pop it, right? Now, what will be the next node? The next node will be whatever is the favorite person of the current node, right? So int next will be equals to in the favorite, whatever is present at the current index. This is going to be our next node, right? So now before we remove this current node, we need to update the depth of next node, right? So for that, outside, let's take a vector for storing depths also. So vector int depth, right? And the size will be equals to n, and initially we can keep the depth of all the nodes as 1, as we saw earlier, right? So for the next node, we need to update the depth, right? So we will update the depth of next node, and as I said, we will always take the maximum depth, right? So we will take the maximum of depth of next node, and whatever is the depth of current node, that plus 1, right? So whatever is the maximum of these two, that will be the depth of our next node, right? And as we are removing the current node, we will decrement the in degree of next node by 1, right? So now if the in degree of next node becomes equals to 0, then we will push it into our queue, right? And if it is not equals to 0, then we won't be pushing it, right? So if you see over here, we are just taking one node always. Why? Because as we said, one node will always have only one outgoing edge, right? So this is our BFS. Now when this while loop finishes, then we need to check all the nodes where the in degree is still not 0, because all those nodes will be forming a cycle, right? So now we will be identifying two things. One is the longest cycle where the length is greater than 2, and one is all the two length cycles, their sum, right? So we will keep these two variables for that, right? Now we will run a for loop of I starting from 0 going till n and then I plus plus. Now inside this we will check that if the in degree of ith node is equals to 0 already, then we will continue because those nodes are already visited. But if it is not, then that means it is forming a cycle and we need to identify the length of that cycle. So we will take a variable length equals to 0 initially, and our current node will be the ith node, right? So now we will run a loop for our cycle, right? Now inside this, we will make the in degree of current node equals to 0. We will increment our cycle length by 1, and now our current node will become whatever is the favorite node of the current node, right? Basically, whatever is our current node, whatever is its favorite, that will be our next current node, right? So this is what we will do. And when are we going to stop? So our cycle will finish when we encounter the node whose in degree is already 0, right? So here we will run this loop till the in degree of current node is not equals to 0. As soon as it becomes equals to 0, then that means the cycle is finished. We have come to the starting node now, right? So once we are out of this loop, in the length variable, we have the cycle length. So we will check that if this length is equals to 2, then we will have to add it in the to cycle variable. In this, what are we going to add? We are going to add the depth of our ith node and its favorite node, because if this is a cycle of length 2, then the two nodes in this cycle are the ith node and its favorite node, right? So we will take the depth of these two nodes. So in this, we will add the depth of ith node plus the depth of ith's favorite node, right? And if the length of our cycle is greater than 2, then in that case, in the longest cycle variable, we will take the maximum of longest cycle length, comma, this particular length. And at the end here, we can simply return the maximum of 2 cycle, comma, longest cycle, right? Let's try to run this. So here if you see, this particular loop is running n times for storing the in degrees. This is running n times for storing all the nodes with in degree as 0 into the queue. And then here we are applying BFS, right? So now here in the worst case, it could consider all the n nodes. Each node will be visited exactly once. So this will also run n times. And then here this loop is running n times. And inside this is checking the cycle length. And wherever the in degree is 0, we are continuing, right? So here also each node will be visited exactly once and it will run n times in worst case, right? So here the time complexity will be order of n. And if we consider the space complexity, so here we have taken an in degree vector equal to length n. Here we have taken a depth vector equal to length n, and we have taken a queue. In this queue, we are storing all the nodes with their in degrees as 0. So in the worst case, it can store n nodes, right? So we can say that the space complexity over here will be order of n. So let's try to submit this now. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.